Hello. Good morning. Hello. All right. So if there's no requests, I'm doing the lab. Ew. Okay. So we'll do the warm up first very quickly. Oops. So we have the list here, and we want to get this element 99. And the question is, how do you get it? And the answer is, well, it's the third element of L, meaning the element at index 2. So L at 1 would be 2, rather, would be the element at 2. And then if you want to get the 99, it would be L at 2. So this guy at 1 in order to get the 99. So that is the 99. All right. So now we want to get nums. So it takes a list that's like this, and it extracts the 92, the 98, the 99, the 95. So the easiest way to do it is with append. So I'll do it with append. So I'll start with an empty result list, and then I'll append the 92 and the 98 and the 99 and the 95. So here I need to iterate through L. So that means get this one and then this one and then this one and then this one. I could do it with an index, or I could just say for row in L. So that will make it so that row, first of all, first it's this, and then it's this, and then it's this, and so on. And I'm going to say, okay, I need row at 1. Let me print it first, and then I'll append it. So right now, it's just going to print stuff. Put it in the main block. I'm going to say get numsl, and it's going to print it. And the reason it's printing it is, again, like row is first this, and then it's this, right? And then it's this, and then it's this, and so on. So now instead of printing, what I'm going to do with row S1 is append it to res. So I'm going to say res.append row at 1. Let me print result. Like so. And then I'll also return it at the end. So I'm printing just for debugging purposes. So this is what happens, right? So res, first it's 92, and then it's 92, 98, and so on. So, okay. So now I can say result is this. I'll comment out the print. Oh, and the result, if I print it like this, is going to look like so. So again, hi, the people in the stream. I don't really look at the YouTube comments, but if you can post on Discord, or you can join the Zoom and you can ask questions, or we can just hang out, that's fine as well. Okay. So the next thing I want to do is lookup. So I want to take in. Good morning, Eric. Kind of morning, yes. So I want to do lookup. So what lookup does is it gets a number and it gets me the corresponding value. So in lecture, we saw something that's like that with dictionaries. Here, we're doing it with a list of lists. So I want to be able, so say lookup. So I want to return the string that corresponds to number num. So for example, look up L. So by L, I mean like this L. 98 should be 180. In quotes, because kind of those are all strings, not that it matters much. So how do I do it? So I'm going to, again, go through the rows. And now I have row at 0 and row at 1. And what I want to do is I want to say if row at 1, so this guy or this guy or this guy, if that matches num, then I want to return the corresponding string. So that's row at 0. So that's exactly what I'm going to say. So I'm going to say if row at 1 is equal to num, return row at 0. So that's all there is to it. So if I find a match, so row first it's this, and then it's this, and so on. If I might find a match where row at 1 is equal to this, I just return row at 0. I don't think I said what to do if nothing match. I return the first value. If there are multiple matches, I'm doing that, right? So if I see a value, I return it right away. Return none if there are no matches. So that does it automatically, right? So if the function doesn't return anything, then that means that it's returning none. I can do it explicitly. There is no harm in that. I can say return none over here. Make sense? All right. Let me just pause for a second and pour some coffee. So, okay. So that's kind of the warm-up. So I'm now going to do, I guess, the Hopfield networks. So here we have the Hopfield network from last week, and there is actually, let me kind of do, because I was doing the slides in order to post it like for people outside of U of T as well. I'm not quite done with the slides, but I might as well quickly go through them. So that's going to be kind of like a bit of a repeat of what I said before. So the goal of, Hopfield networks is to do something that's like, not literally, but a little bit kind of analogous to the kind of thing that brain does, as opposed to the kind of thing a computer would ordinarily do. So a computer ordinarily would just store the memories as a list of numbers. So if you happen to be kind of remembering the digits of pi or whatever, it's literally a string of numbers. Otherwise, it's encoded as numbers in some way, but it's basically a list. On the other hand, the way the brain works is it has kind of neurons in it. So the neurons fire electrical pulses, and they communicate in the sense that if one neuron starts firing, then another neuron that's in proximity is sometimes observed to also fire. So they basically communicate between each other somehow, and somehow that gives rise to, memories that we experience, or so it seems. So Hopfield networks are a very early attempt to show a mechanism that resembles what we think the brain kind of acts like, and showing that that kind of mechanism can store memories and retrieve memories reasonably efficiently and with reasonable fidelity. So this is the kind of simplified Hopfield network that we settled on. So, the axis here, x0, x1, x2, they kind of represent the neurons. We call them sometimes the nodes, sometimes the units, the neurons. And then between them are connections. So between actual neurons in the brain, there are also connections. So kind of synapses, stuff like that. And then we have the weight on the connections. So that is also kind of like what we think the brain does, in the sense that different neurons are connected more weakly or more strongly. Okay. So now specifically the way we want to go about things is we want to say there is this energy function, which if it's very small, then the corresponding x's are the memory. So we say that the x's in this case can be either -1 or 1. And we say that the energy specifically would be, x0 times x2 times the weight between x0 and x2, and x0 times x1 times the weight between x0 and x1, and x1 times x2 times the weight between x1 and x2. So that is what this formula means. In general, it would be, of course, more x's, in which case it would be all the combinations of connected x's where the index of the left one is smaller than the index of the right one, but it's just all the x's. Okay. And then we're saying a memory is a combination of x, so x0, x1, x2, such that the energy function is small. So like this. And then we implement it in Python like so, right? So we just say, okay, we have the x's, we have the weights between the x's. So for example, the weight between x0, x1 would be w01, because between x0 and x1. And that means that for a network with 3 units, what we're going to have is minus the sum of those 3 terms, just because there's 3 distinct pairs of x's in this particular network. So that is going to look like this. So the difference between this and what we saw in lecture is that instead of plugging in W01 the way it's plugged in here, it's a variable, right? So I could, in principle, try and change it. Okay. So now what we saw is that if you know the possible values for x0, x1, x2, you can just print out all the possible values for all the possible combinations of x's. And the way you do it is with a nested loop, right? So you just say, well, like x0, it's going to be at -1 at first, and then 1. And then for x0 equals to -1, we try all the possible combinations of x1 and x2. And we just print out the energy for x0, x1, x2 for the particular x0, x1, x2, which all could be either 1 or -1. Let me check Discord real quick. Okay, still kind of morning. Okay. So, all right. So that's like this. So, and that's what the output is going to look like, right? So like for some x's, the energy is going to be smaller, and for some, it's going to be larger. So for the particular network that I gave you, all the energies that are small are -2. It's a small network, so there's got to be repeats there. Okay, so we refer to this guy and this guy and this guy and this guy as memories, right? So the things that are stored, the way they're stored is, if you want to retrieve them, you need to find the x's that minimize the energy, and those would be the memories. So the goal for the question in the lab is to store new memories, right? So what does it mean? It means that I want it to be the case that I take this network, I adjust it a little bit so that the memories are still there, that are the old ones, but I also want the new memory that I want to store to result in a small value for the energy. Okay. So I don't want to mess up the weights too much, meaning I don't want to change the weights too much, because if you don't change the weights too much, then the old memories are still retained. And also there is no new kind of imaginary memories that you might have as well. If you just change the weights, you just have new minima. And the strategy is like this. So you want to make this guy very small. So how do you do that? Well, in order to make the whole thing very small, you need to make this as large as possible, and this as large as possible, and this as large as possible. Because like in order to make minus something small, you need to make this something itself big. So how do you make this product big? Well, if the product x0, x1 is positive, then in order to make this even bigger, you'd make w01 a little bit larger. On the other hand, if something like this product is negative, then you want to make w02 smaller in order to make the overall thing smaller. Okay, so that is what we want to do, is we want to just write code to adjust the w's a little bit with the if statements, so that the new memory is it corresponds to something that looks a little bit like a minimum. So the thing that we want to store here is -1, 1, 1. So, okay. So let me quickly copy the stuff from here. So this is the energy. I'm not sure if it copies nicely or not. It does not. Okay, so we have our energy. And we have our parental energies. So notice that here, if I press enter right now, it's indented correctly. So what I do here is I just press home on a PC that works. So Command Shift left on a Mac, and then I press backspace and it's here. And now I press enter and now it's indented nicely. I think I need to press backspace here as well, possibly. Maybe not. Okay, so that's that. So now what I want to do is, yeah, Claire.
Hi, I'm sorry, could you post the Discord
yeah.
invite in the chat, because the one on
Oh.
Piazza is not working for me.
Oh, sorry about that. Sure.
No, it's okay.
So okay, invite people. Okay. Okay, sorry, like you probably said in the chat and I wasn't looking. Okay, I now see the chat as well. Yeah, I posted it now. Okay, and while I'm in the chat, I guess I'll try to answer the question. So if we have a question about Hopfield network midterm, will you give us the basic E and parental energy function, or should we know how to derive them? So you can't really know how to derive them. So if I don't give you E, then I would give you the formula with the sigma. Parental energies, I think, is a legitimate question to ask. It's just like all it is trying all possible combinations of x0, x1, x2. We've done it lots of times in several different contexts. So that you should definitely know, not in the sense of knowing parental energies, but in the sense of knowing how to do all combinations of x's.
Yeah, that makes sense. I was just wondering, because like for the lab, we were building off those functions.
Yeah, totally.
So
And, I mean, so like it depends on the question, right? So like you want to ask something reasonable, and sometimes the something reasonable needs some kind of context.
Yeah, that's fair.
So, yeah. Okay.
Thank you.
And the Discord invite is working.
Yeah,
okay.
It worked.
Okay, cool. Okay, all right. Cool. All right. So what we want to do now is we want to adjust the weights there. So the W's so that, sorry, I forgot the number again. So that we can store minus 1, 1, 1. Okay. So I'll name it just update. And it would take x0, x1, x2. And it would take W1, W2, and W12. And what we want here is just 3 if statements, right? So we want to say if x0 times x1 is greater than 0, then we want W1 to be slightly larger. I'll be nice about it, and I'll add alpha. Otherwise, I'll subtract alpha. And I'll do the same for all the other ones. So this is x0 times x2, and this would be W02. And this is x1 times x2, and this would be W12, because it's the weight that corresponds to the connection between x1 and x2. So, okay, so the question that I was being asked there is just to do one update. So what I'll do is I'll say alpha is like this, and then I'll print all the energies before the update, and I'll print all energies after the update just to see what happened, right? So okay, so that would be, it's a little bit annoying to have to pass all of those things around, but we can copy paste. So that would be like this. And that would be like this. Yeah.
My question is just, is the value 0.1 completely arbitrary, or is that like?
Yeah, so I mean the answer is it's only not arbitrary in the sense that I checked ahead of time that it works. In practice, if you're doing something like that, you would kind of figure out what works.
So like, is that, I know you were talking about magic numbers or whatever. Would it be better to make alpha a parameter and then be able to input that from the if main block?
Yeah, completely. So I just kind of got tired of having, like 6 parameters.
Yeah, no, that's fair.
But yeah, completely. Yeah, like it would arguably better to set it in here. In fact, let's do that.
Okay.
Now, of course, kind of all it does is shift alpha equals 0.1 to here, but so okay. So we have this update. So we want to store it for x equals to minus 1, 1, 1. So that means that here, well, so this is maybe more appropriately named like try update, because it's not really going to update the W's yet, right? So x0, x1, x2. Like so. And now we have to say x0, x1, x2 is equal to minus 1, 1, 1, and W1, W2, W12 is equal to whatever it was in the slot. Oh, actually, do we have it anywhere? No. So here it looks like this. So 0, 2 is so 0, 1 is 2, and then minus 1 and 1, right? Yeah, there's something on Discord. Yeah, okay, so it's not really so here's kind of, if you look at the front pages from the past midterms, what it says is that doc strings are not required, but as you say, they may help us read read your code. Now, we do not grade you on the doc strings, and sometimes people kind of try to just like write a comment instead of writing code, and we just say no, because, you know, like especially in the beginning, like a lot of what we're teaching you is code, and it's like not fair to other people to kind of give credit for English rather than Python. To other people, meaning, you know, the people who follow the instructions and try to write Python. At the same time, like, it can't hurt. So, or, well, I guess like sometimes it can, in the sense that if you know, like, if you kind of try to fool the TA into thinking that you know what you're doing, and then like in English you say something that indicates that you definitely don't, I suppose that could hurt, but like that happens very rarely. You know, if you find that it helps you write code, then for sure you should do it if you have the time. Otherwise, I don't think that should be the priority, but if you find that you have the time on the midterm to do that, then, you know, why not? It's probably, it might help, it might, like, in practical terms, it might help. It's very unlikely to hurt. Again, we try to set up the grading so that it doesn't help, like it only helps us save time, not like, you know, not anything else. But in practice, like, I could imagine a TA kind of looking at the English and saying, oh, that kind of makes sense. So yeah. All right. So, okay. Yeah, you also have your hand up on Zoom. I'm not sure if that's the same question or a different question. Okay. So we can now run this. Parental energies. I didn't say alpha. Yeah, go ahead.
Sorry, it's showing. Okay, there it goes. It wasn't going down. I didn't have a question,
Okay.
but okay,
Okay.
sorry about that.
All right. Okay. Cool. Okay. So parental energies takes 3 positional parameters. Oh, because it doesn't need the axis, of course. Yes. I don't know what I was thinking. Okay, so parental energies is like this. Okay. And what we have, so I didn't print like a separator here, which I will do now. So that is kind of what it looks like. So so the first thing to say here is that not much has changed, right? So, you know, maxima are still maxima, minima are still minima. We were trying to make it so that -1, 1, 1 is a little bit smaller, and it is indeed a little bit smaller, as is 1, -1, -1. Okay. So the next question is basically saying, well, do the same thing, but repeatedly, right? So let's do that in a separate function. So one could kind of use try update as a helper function, but that would require either awkward coding or something that we haven't done yet. So I'll just do it as a separate function that replicates some code. So I'll just say repeat for num iterations. Just do this. And now I don't want to be printing all energies twice. So I'll just comment this out. Yeah.
Sorry, why isn't it nemitters -1?
Well,
I think I'm
mean,
just
I didn't
confused.
even say what I didn't even say what nanometers is. So like you could well imagine that they could say nanometers -1, but this is
Oh,
just
okay.
saying, repeat this many times. If you want to
Yeah.
repeat this many times, you go from 0 up to nanometer -1, not including nanometers, which means that for ion range nanometers actually makes it, 0, 1, and so on, up to nanometers -1, which is nanometers times. Sorry.
Okay, sounds good. Thank you.
Yeah. Okay. Right. So let's just do that. So instead of doing try update, we'll do try update loop. Try update and then say loop. And here's what happens if you do the loop 4 times. So you have -111 does get to be, a smallish number that's kind of comparable to the old memories. The old memories are still the smallest ones, but they are kind of creeping up a little bit. And there is also one memory that's fake news, but that's life. So we could try to do more iterations. So let's do 8, for example. And what we have here is -111 is now the smallest memory, the X that corresponds to the smallest energy, along with this guy. And then those are still pretty small. So that's like that. Okay, and that's kind of all there is to this question. Okay, so now I think we're doing tic-tac-toe. Oh, sorry. So there was like another thing. So use the function to store note that function. So here, what I meant to do was that when you are finished updating the loop, what you need to do is you need to actually return the memories, right? So I'll say like return W01, W02, W12 as a list. In principle, you could just return it as something called a tuple without the square brackets, but we're not going to do it right now. And that means that you could say, result is equal to this, and then you could say W01, W02, W12 is equal to result 0, result 1, result 2. And that's just multiple assignments. So you could just say result 0 equals to W01, result 1, the other way, W02 is equal to result 1, W12 is equal to result 2. And that would be the new weights. Now, actually, what you can do, we just haven't done it yet in class, is say something like this. This is called unpacking, and that also works. So this guy is just the same as this guy. So this is what you were meant to do in the lab, but in a few lectures, I guess, we'll do this kind of thing as well. All right. Okay, tic-tac-toe. So here we want to download TTT. So this kind of just like in an annoying way prints the board. This function is kind of interesting. So what it does is it makes what we call an empty board, which is a list of lists, and then each list contains 3 empty strings. Well, not empty, so they have a space in there, right? The way we do it is by starting with an empty board, and then 3 times we append this list that contains the single element space times 3. So this works the same way that we saw in the very first lecture how strings work. So it just replicates the element 3 times. So here we have a list with the same element, the space, repeated 3 times. And then we just start with the empty list, we append this thing, and then we append it again, and then we append it again. And that gets us the empty board, or what we use in order to represent the empty board. So the way the boards work is we just print, this guy goes here, and then this guy goes here, well, here, and then this guy goes here, and then this guy goes here, and this guy goes here, and so on. All right. So, okay. So now we have kind of the print board in legend, and here we're printing the empty board. So the legend just means kind of like this thing, which indicates, which square has which number, so that you don't have to think about it. And then we can also set the board to something like this. And this would just say, print this guy. And that's what happens. So this guy is printed over here. Okay, so what do we want to do here? So in part A, so write a function that takes in an integer square num and returns a list chord such that board chord 0, chord 1 equals x, would put x in square num. So essentially what we want to do is we want to say for number 1 through 9, figure out what the row number is and what the column number is. Okay, so one way to think about it. So I'm looking at this guy here, and I'm looking at the numbers. Is I actually want to go back to the Python way of numbering things. So I'll start with 0. And then if I'm starting with 0, then I can say, okay, so if I do the number divided by 3, I'll get 1 here, and I'll get 0 here, and I'll get 1 here, and I'll get 2 here. So that will give me the row number, right? So the row number is 0 based index divided by 3 with integer division. Or you could say 1 based index minus 1 divided by 3, because 1 based index is 0 based index plus 1. Okay, so that's the row number. The column number, if you think about it kind of also in terms of division, like if you look at it, you're going to say, okay, like 0 mod 3 is 0, 1 mod 3 is 1, 2 mod 3 is 3, 3 mod 3 is 0, 4 mod 3 is 1, and so on. So this goes like 0, 1, 2, 0, 1, 2, 0, 1, 2. And that's exactly how the columns go, right? So it's column 0, column 1, column 2, column 0, column 1, column 2, and so on. So that means that you can use the same trick, except with mod, in order to get the column number. So that's what it is. So, and that's not the only way to do it, but that is one way to do it. So get chords Oh, this is square numbers. So this is like this, and we'll return a list. That's the row and the column, and then the row is n-1 divided 3 with entry division, and the column is n-1 mod 3. So that's kind of like the most elegant way of going about things. You could also imagine, like if you wanted to, just having 9 if statements. That seems not difficult, right? So just say, like if n is equal to 1, then you would return 0, 0. And then if n is equal to 2, then you would return, 0, 1, and so on. So that's like not something that I would recommend, but at the same time, this is just 18 lines of code. So not anything that's too difficult. Yeah.
Sorry, could you really, really quickly explain the double slash and the not thing again? Like really quick?
I'll try. So
No, like what they mean.
yeah. So basically, double slash is integer division. So that means kind of the division that you would probably be taught first, right? So for example, like 8 divided by 3 is, 2 point something, right? 2.67. But for positives, you just round it down. So this means that 3 fits inside 8 twice, with some leftovers. Does that make sense? So 8 is approximate 2 times 3. In fact, 8 is exactly 2 times 3 plus 2. And the 2 is this 2. This is a little bit unfortunate. Let me do 7 instead. So 7 is also like that. And then this is 2 times 3 plus 1. And then 1 is the remainder. And then that means that 7 divided by 3 with integer division is equal to 2. And 7 mod 3 is equal to 1. Okay, and this just means that, in integer division, 7 divided by 3 is 2, because, in exact terms, it's 2 point something. And then that means that 3 fits twice into 7 plus a little bit of leftovers. So here we're saying this is how much leftover.
Okay, so all that like the not thing does is give you the remainder.
Yes. Yeah, mod is the remainder. Yeah.
Mod, yeah.
Yeah.
Sorry.
Yeah.
Thank you.
Yeah, okay. Sure. Okay, all right. So we're here. So you could also, so this is kind of from Friday's material. Again, kind of this is kind of the thing that I intended, right? But with Friday's material, you can also do something like this, so like num2 chords, and then you can have a dictionary. And in the dictionary, so this is like a little bit more concise than square num2. So you could say, 1 is 0, 0, and then you would say 2 is 0, 1. And then you would say 3 is 0, 2, and you would say 4 is 1, 0, and so on. And then you would just like return num2 chords at 10. In fact, like you wouldn't need the function, you would just need this dictionary. So again, like something you could do for smaller boards, obviously for larger boards, that would make it harder to write down.
Yeah, okay. I don't know if you just haven't gotten there yet, but why did you say mod D?
I actually, yeah, so I like that was a few minutes ago, so let me go back to that. So
okay, I
what
didn't know
I'm
if you
saying,
hadn't
yeah. So this is this, right? So if you think about n minus ones, so this is the n minus ones, right? And then if you just think about one way to think about it is what's the pattern? So remainder of any number divided by 3, it goes 0, 1, 2 at first. And then this is again 0, 1, 2. And this is again 0, 1, 2. Right? Because 6 is evenly divisible by 3, and then 7 has remainder 1, and 8 has remainder 2, for example. Right? So that's just kind of the pattern. And then the pattern that you want for the coordinates is the same, right? So you want, I wrote down like almost half of them, so why not? So this is what we want, right? Is we want, 1 is 0, 1, this one, I guess, is 0, 0, and then 2 is 0, 1, and 3 is 0, 2, and 4 is 1, 0, and 5 is 1, 1, and so on. Does that make sense so far?
Yeah.
Okay, so now we just look at, okay, like what's going on here? Well, we want the row numbers to be, 0, 0, 0, and then 1, 1, 1, and then 2, 2, 2. And then we want the column numbers to alternate 0, 1, 2, 0, 1, 2, 0, 1, 2. Right? Like that's just like what this shows. And then kind of one way to approach this is, well, like that's exactly what integer division and mod do, right? It's that this is saying, if you divide it by 3, then that's going to be, all of those are going to be 0, all of those are going to be 1, and those are going to be 2. So that makes it convenient to store rows. There is a deeper reason why that happens to be the case, right? The reason it happens to be the case is I'm saying if I am, 4 squares in, then how many rows do I need in order to store all of those guys? And the answer is, well, if each row takes 3, then it's 4 divided by 3 plus a little bit. Right? So 4 divided by 3 is 1, and plus a little bit is a little bit of the second row as well. Does that make sense?
I'm a little confused about, like, I get what you're saying about integer division and mod, and like how they allow us to represent the rows like in that form that you showed on the TMP5. But I don't know, it's like it's hard to grasp, and like I don't think I would be able to see that by myself.
Yeah, I mean, that is kind of why I gave it out in the handout, right? Is that, like I think it's hard to see by your I think if you're not used to this kind of thing, which like there's no reason that you would be unless you're like working with specifically this kind of like two-dimensional table data, which like almost nobody is in the class. Certainly. Like there's no reason that you would like if you're thinking to yourself, like, how would I come up with not this, but something like this on the test? The answer is, like that would be hard unless it's like specifically this thing with two-dimensional tables.
Okay.
The way you would come up with it is you would remember it from the lab. Yeah.
Okay, thank you.
And so like that's like a completely legitimate question, but there's not like you could imagine, a variation of that would be like, like how do you do that? But instead of a square, you have like a cube, right? So that's kind of hard to draw, but like you have kind of like cube that's subdivided into little cubes. And if you're playing like three-dimensional tic-tac-toe, right? and you have like the numbered, the little cubes are numbered, and then you also want the coordinates. So that would be kind of like this, but I don't know if there's like many more kind of variations on this anyways. Okay, oh, is someone tagging me? Oh no, that's just an announcement. Okay. Okay. All right. So this is like this. And yeah, so does that kind of make sense now?
Yeah, I think
Okay.
that's a little better.
Yeah, okay.
Thank you.
Okay, cool. All right, so that's num2 chords. And now what I want to do is I want put in board. So that means that I want to take the board and I want to basically modify it, right? So I want to be able, so if I were to make it directly, it would be something like, I want to say, board at 1 at 0 equals O. Right? So board at 1 is this guy, board at 1 at 0 is this guy, and instead of a space, I want there to be an O there, and print board and legend again. So that would look like this. I'll print a few new lines. Okay, so that's like this. So I want to make a function that's like this, but where I put in the number of the cell and it figures out the coordinates, and then it puts in, oh, I didn't write get coords here. You write get coords. So now I want to, so this is called put mark on board. And this will take board mark square num. So what I do, I get the coordinates. So I'll use the shorthand that we used before. So I'll say, row column is equal to get coords square num. So now I get the row number and the column number inside the board. And now I'll just say board at row at column is equal to mark. So now instead of doing something like this, I can say board, sorry, so put mark on board. And here, like the idea would be that when I'm playing the game, I'll just say I want to put the O in number 4, and I can just use the function to do that. And that does the same thing. Right? Okay, so my voice is getting a little bit hoarse, so I'll take a break until, sorry about that, until 12:02. Please don't go away, or I'll be all by myself. That would be sad. Okay, I'll be back. Or like if you have to go, I know that like maybe you planned from like 11 to 12. That's fine as well. But at any rate, I will be back at 12:02. Yeah, sorry about it. Okay, see ya. All right, I'm back. Hello. So, okay, so we were doing put and board. So now what we're doing is ask the user to enter coordinates X and O so that two users, or like the one user can play against each other, right? So how to do that? So what we want to do is we want to have a while loop that basically knows whether it wants to put X or O next. And then it just, yeah.
I'm sorry, I have one basic question about the last Dev put mark and board. Do we have to put board row call equal to mark on line 35, or can we put mark equal to board row call?
Sorry, what
Like
was
just
the other option?
Like flip them around. Like, does the
Oh,
order
you
matter?
cannot, yes, the order does matter, right? Because,
Okay.
so here's basically the issue. So like the usual thing that you say is something like A is equal to 5, right? And then that means that A has become 5. Of course, like if A was 7 before, and then you say, A is now 7, and then you say it equals to 5, of course, like 5 is still 5, right?
Yeah.
So it's A that's, so 5 has not become 7, A has become,
Oh,
so,
okay. Yeah, I
so
see.
yeah, so it means like take the right-hand side, put in the left-hand side. Yeah.
Okay, thank you.
So if you have, just kind of to maybe belabor the point, if you also have a B, something like that, and A is 5 and B is 7, A equals B means A has now become 7 while B is still 7, while B equals A would be the other way around.
That makes a lot of sense. Thank you.
Yeah. Okay. All right. So, yeah, so we're doing, something like this. So here we'll make an empty board. And now we need to, so I'll do it like this. So I'll do like mark is equal to X. And then I'll do while true, basically. So I'll ask for the input. So square would be input, enter square number. And now the first time that I do it, I'll just want to put the mark in the board. So this would be board, and this would be mark, and this would be square, like this. And then the next time, so if I run this, right? So I think it's worth maybe running this. So I'll say like friend board and legend, and I'll print a few new lines just so that it's, yeah. So that's like this. And now if I run this, so Control R to comment everything out. I didn't put like a column there, but whatever. So like square number 4, okay. 5, okay. 1, okay. So that just puts X's everywhere. So let me just, so Control I or Command I in order to interrupt, by the way. So, yeah.
Sorry, I just have a question about the parameters. So why can you like do put mark and board parameters board mark and SQ, but where you've defined the actual function, it's board mark and square num. Why are you allowed to change the parameter?
The answer is that it's not just that I'm allowed to change the parameters, it's that I'm allowed to just have literally numbers or literally strings.
Oh,
So I
that's
could
fair.
say something like that as well, right? So the question is what the values are.
Okay.
Yeah.
Okay, thank you.
Okay. So that's like that. So now what I'm gonna do is like it almost works, right? So I'm putting in the square numbers and it plays tic-tac-toe. The only thing is that it always puts in X's, so I want to alternate. So the silliest way to, or not silliest, I guess, but the kind of like long way to do it is I can say like if mark is equal to X, then mark is equal to O, and it's not that long. Else mark is equal to X, right? So basically I want mark to become O if it was X, and I want it to become X if it was O. So that's one way to do it. A kind of one-liner to do it actually kind of goes back to lab 2. So if I define previous mark as O, then what I can do here is I can just swap mark and previous mark every time. And then if it was X, it becomes O. If it's O, it becomes X. And now I can play it. So I guess it would be nice. Yeah. So okay. So I guess like it would be nice to print it the ones outside the loop so that I know what I'm playing. So here I can play 5. And then the next time I play 2, it's going to be like this. If I play 3, it's going to be like this. I play 7, it's like this. Play 4, it's like this, and so on.
Sorry, I'm confused about the while statement you have. What, like, you're saying while true, but while
Yeah.
what is true?
So this just doesn't stop, right? It also doesn't enforce. So while true just means like if it's true, then keep going. And of course, this is always going to be true, so it's just always going to keep going. There's no condition there right now for how it should stop.
Okay. Okay. I think that makes sense.
Yeah. Yeah. All right. So, okay. So now what we want to do is, yeah, I think that's done. So now we want for the computer to play against the user. And the way we want to do it is we want to get the free squares on the board. And then once we gotten the free squares, we're going to do kind of various things. So by free squares, we mean the coordinates of the squares that don't have a mark in them. So how to do that? So it's basically the same kind of thing. So as we did several times before, where we start with an empty list and then we add stuff to it. So what kind of stuff? Well, we want to try every possible row, every possible column. So the pattern there is 4 row in range 3, 4 column in range 3. So here we got like every possible combination of row and column. And then we want to add it to res if the square row column is empty. So that means
I just want to clarify, is it 3 because
0, 1, 2.
it's 0, 1, 2? Okay.
Yeah. Yeah. Okay. So we're going to say if board at row at column is equal to the space, then that means it's empty. So we'll append row column to the result. Make sense? So we go through all the possible rows, all the possible columns. So like 0, 0, 0, 1, 0, 2, and so on. And then if we see an empty space, we append it to the result.
I just ask for append. Does the thing that you're appending to, I'm guessing it has to be a list, right?
Yes.
Okay, just sure.
Yeah. Yeah. Okay. So, all right. So that builds up this kind of deal. So this kind of deal to kind of be clear so this kind of deal to be clear what it's doing, it's saying 0, 1 is empty, and then 1, 0 is empty, and 1, 2 is empty, and 2, 1, and 2, 2. So now with that, we can make a random move. So this would be board, and I think it specifies, so it says like what mark to put there. So how do we make a random move? Well, what we can do is we can say, okay, so free squares is the free squares on the board. So it's a list like this, and then we get a random index in this list, so 0 or 1 or 2 or 3 or 4, and we return this list at that random index. So this is just a recipe for how to get a number between 0 and n minus 1. Right? So does this make sense? So if you import random, so random.random is just a number between 0 and 1. And then random.random times, let's say, 5 is a number between 0 and 5, not including 5. And then if you convert it to an integer, then it's a number between 0 and 5 minus 1.
That makes sense. And random is just a integer? Or sorry, a
yeah,
variable?
it's a variable. And then we return
integer.
Yeah, and that's an integer, that's right. And then we just return a free square at random index. Right? So we got our free squares in this form. We got a random number that's between 0 and the length minus 1. And we're getting something that's in this list.
Yeah. Could the midterm involve like imported things like that?
Or I mean, it could certainly involve so the only thing that we've imported are random
like
math
and
and time. Yeah. So
okay.
like I'm not gonna ask people to like, I guess kind of to math. So I guess kind of like the expectation would be that not that people would remember anything in particular from like math dot, but people should probably remember that there is a random.random and a time.time. But other than that,
Okay, thank you.
Yeah. All right. So that's make random move. So now we want to play with it, right? So this would be play against random. And we'll copy this. So I'm saying board is make empty board, and then I'm saying our I guess I'll do like user mark is X and computer mark is O. And then for now, I'll do while true. And then I'll ask the user for input and put their mark on the board. So that's the same. So I'm saying enter square number, put mark on board. So this would be user mark now. And then I'll have the computer also play a turn. So I'll print the, well, no need to print the board, I guess. I'll just ask for the computer to make a move. So I'll say make random move. And I'll say board. And I'll say computer mark. And that's it. So we can play against it. So here I can say like 5. Oh, I didn't say print board. No, it did play, it just doesn't show what it played. So I'll play 5. And I guess it didn't make a random move. What's going on here? So make random move. Oh, because I said return, and actually I should have said like board at the free square at 0. So let me do it. Row column is equal to free square random randend, and then board at row column is equal to mark. So I returned the coordinates instead of actually like making the move.
Oh, wait, sorry. Could you explain just a bit more in detail what you did there?
Yeah, so free square random end is this kind of thing, right? So like 2, 2. And then I got row is 2, column is 1. So this is kind of like the thing that I've been doing for this lab, but you could also say something like row is equal to free square at random index at 0, and then column is the same at 1.
But what would you like? Would you recommend the one that you hashed out there?
I mean, it doesn't matter. The same.
Okay.
Yeah. So, okay. So, okay. All right. So let's play that. So 5. Okay. And now it played something, and then I'll say 6. And now it played something, and say 3, and it'll play something. I'll say 9, it'll play something, and so on. Okay. So that's just kind of a random free square. So the next thing that we asked for was is row all marks, and that would return true if row I is all marks and is column marks. So that would return true if column I is all marks. So the function here is board column I. Right. So how can I do it? Well, I need to check board at row I0, board at row I1, and board at row I2. And sorry, let me just check my phone real quick. All right. So so basically what we want to say is board at row I at 0, and also board and also R and the way to do it is to say, okay, so for J in range 3, the reason I say J is just kind of, I could have said I, it's just that row I is being used for something else. So I can say so this is like, I could have said I, right? It's just like I want to use something that sounds different. So if row I at J is not equal to mark, I return false. And if I've never returned false, that means that they all are equal to mark, so I can return true. So similarly, if I'm saying is column all marks,
Sorry, I'm just a little confused with what row I is.
so row I would be 0 or 1 or 2. So I'm asking, like, is row number row I does it consist of all marks?
Okay, so when you say for J in range 3, J is also 0, 1, 2.
Correct.
So I guess you're just getting coordinates then?
That's right. Yeah. So so
Okay.
row I is fixed. So I'm for example saying, like, so there's no row like that here, but I'm saying, like, this row, it all consists of just marks.
And where do you like input that so it knows to look? Like, you know what I mean? I don't know how this
I think you're
function is.
asking, like, where do I specify row I? And the answer is
Yeah, that's what I mean.
it's a function. I want to be able to specify any row I that I want.
Yeah.
Yeah. Okay. So when I use the function, I'll actually plug in all of them as well.
Okay.
Yeah. Okay. And then
Okay.
for column I, it's going to be the same, except it's the column I that's fixed and the J here that changes. So other than that, those are the same. Does that make sense? So here I want to check, like, for a fixed column I. So for a fixed column index, I want to check row number 0 and row number 1 and row number 2 and J ranges like that.
Yeah, that makes sense.
And here I want to look at all the columns. Okay. Okay. So now I want to write the function is when, and I think that takes yeah. So so I'm going to say is when mark, and that's going to be board mark, and I want to return true if player who plays mark has 1, right? So what do I need to do? I basically need to check, like, is it the case that they won because of the first row? Is it the case that they won because of the second row? Is it the case that they won because of the third row? And then because of the first column, second column, third column, right? So I'll do that. So if any of the rows are all marks, I guess let's say row I here, it doesn't really matter what we call it. Then we return true. And equally for column I in range, this is 3. If column all mark, then we return true. And now there's 2 more ways to win, which is kind of the diagonals. So here, kind of with the rows, it kind of made sense to make a function because there is multiple rows. There's just like one diagonal that's like the right diagonal and one diagonal that's the left diagonal. So you can just do it like in here, I suppose. So
Sorry, I'm confused by your conditionals. You're
okay.
saying if is row all marks colon.
Yeah,
Like if it's what?
because
So,
right, yeah, because the way if statements work is you have this thing, and then if it's true, then you do this. If not, then not. So
so you
you
don't have to
could
say
say,
if this
yeah, so
equals
you
true?
could say equals equals true, but that's the same. Yeah,
Oh, okay.
yeah,
Thank you.
yeah. Okay. Yeah, so I want to check the diagonals. So I want to say if this list is the same as the list that has all marks, then also return true, right? So I'm just making a list of the right diagonal. And then the same thing for the left diagonal. So the left diagonal is board 0, 2, board 1, 1. That equals to the list that contains the mark times 3, then also return true. If you've checked all the ways for it to win and it doesn't win, then it's return false.
So are those two if statements, are they checking for every single row or just two rows? Like
So they're
the
checking
ones that you
for,
just wrote?
so those guys are the two diagonals, right? So it's this diagonal
Okay.
and then it's this diagonal, and there's only the two.
Okay. So do we have to do them for the horizontals and verticals or
No, like that's the horizontal. So the verticals are those, and or do you have to do the loops? No, like you could have written out like 3 if statements.
okay.
Yeah, so
Okay, that makes sense.
it's just that like basically we kind of outsource the if. So we just say, do the if statements, and the if statements are like in here rather than in here in a way.
Okay, thank you.
So yeah, okay. So that is win. And what we want to do now is we want to make the computer take the opportunity to win if it can win right away. Right? So how to do that? Well, the idea is what's the name of the function? So the idea in problem 8, sorry, so let me first kind of improve this guy. So here I can now say in, I guess, play against random, instead of saying while true, I will say, while not is when X, or, well, so like, the only thing that it could be is like, yeah, I suppose I'll do while not is when X, or is when O. Do this. So if one of them has 1, then I'll stop. Yeah. Yeah.
This is a little unrelated, but on the midterm, like our questions structured so that we won't have to go back and change functions like after we've written them, like based on new information that we're getting and set like new question parts.
So certainly there's not going to be a question that's like go back and change something in the question from before.
Yeah,
Because
but
the
like if you're
question from
trying to
before,
use a function in a new question, would
I've
because I
done
can
something.
imagine doing that on paper would kind of suck. So
I mean, like, look, it's like there's not a way that writing the midterm is not going to suck. It's kind of like
no,
if
like that's fair. But I meant just like, should I
so,
expect for that or not?
no, because like, like the alternative to like looking back and changing the thing that you had before is like writing a whole new thing. Like you're going to be writing either way. Wouldn't you
Yeah,
prefer to be
okay.
writing
That's
something that's
fair
kind of
enough.
related to what you've done before,
Yeah. Okay,
So
thank
yeah. So I have like the answer is like I occasionally do stuff like, building on kind of previous questions. I try to make things as independent as possible because, like the downside of, building on previous questions is that if you haven't gotten the previous one, then you kind of don't have anything for the next one. So I try kind of if I see a situation where I can avoid this, but still kind of build on previous questions in some ways, I sometimes do that. But not that frequently, I guess. Yeah. Okay. So we're doing,
Professor?
yeah.
Hello. I just had a quick question about the midterm and how it works.
Okay.
Kind of on like the same boat as what my classmate asked.
Yeah.
But how does like the marking and everything of the midterm work? Like if you is it like if you run the code, if you write a code and if the code runs, then you get a mark, and if it doesn't, then you get a
No,
zero?
so if you look on the course front page and you look at the solutions, you can actually look at exactly what the marking scheme looks like for previous years, and it's going to be kind of the same. So I'm like showing one of them now.
Okay. 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 Thank you.
So kind of like that. Yeah.
Kind of along the same note, say we write something and it works perfectly and we get like no bugs, we get the same thing every time, or like what we're supposed to get every time, but it's done in like a really inefficient way.
That's
What
fine.
is that
So,
usually? Okay.
no, that's fine. So again, kind of or not again, because I'm saying again because I have this conversation often, but you're probably hearing it for the first time. So the midterm is a contract in the sense that whatever it says, that's what you do. So if it says you must make the program be, efficient to this extent, then yes. However, in this class so far, we haven't actually, built up the language for talking about measuring efficiency, which means that there's no way that I could ask for that in the midterm. If you look at past exams, sometimes there is a requirement. So this is called computational complexity. So this is kind of the efficiency. So sometimes it's like it must be this efficient, and then it says like it must be O of n squared. And we'll talk about what that means later on in the course.
Okay.
But so far we haven't got the language to talk about it, so there's no way I can ask about that.
Thank you
So
so much.
in principle, yes. On this particular midterm, no. But
Professor?
only if I ask. Yeah.
Sorry, this is kind of related to the midterm, but also related to the lab that we did yesterday.
Mhm.
For question 5A, I know like when you had to like come up with like coordinates, what was like you gave us a hint and you said that you could for 5A, yeah. You said that like for the row number you could do square num minus 1, and then like you can do like the floor division divided by, right, to get the number of the row, and like sort of the column you'd use to the remainder. Instead, what if you had made a list, and it's like similar to question 3, you made a list of like possible coordinates y and x and like the y coordinate, and then what that number would correspond to. And if
Yeah.
you had done it like that, would you still get a mark, let's say on like a midterm? Because you did it, but you didn't use like the hint that was given, or you didn't really use like the integer type of thing, but you ended up getting the code to run.
Yeah, so I would say if it says hint, it's not, I guess, it's not mandatory. So I would try not to get into this kind of situation where I say hint and then it's unclear whether you have to use it or not, because in practice, what happens if something is unclear, it's like lots of people during the midterm are asking exactly that question, like, do I have to use the hint? So I try as much as possible to make things unambiguous. The rule is, if it doesn't, again, it's like a contract. So like there's no kind of things which are like implied or understood, right? It's like if you fulfill the requirements of the question, then you fulfill the requirements of the question. If it works, it works.
Okay.
At the same time, you do need to fulfill all the requirements. And I would say kind of the hint is not like, if I wanted to say you're required to use this, I guess on the midterm, I would say that. On the lab, I'm not like as worried about people, like interpreting things that way or this way. Like if you don't want to use the hint, I guess you don't have to. But at the same time, the lab is there for you to learn. So like if you don't use it, well, like you're probably missing something.
Okay. Okay. Thank you.
Yeah. All right. Okay. So what we're doing. Yes. So we were trying. Oh, okay. So I was doing, I think, the play against random. And here, so I want to stop if X1 or O1. And in fact, I don't want to be making a random move if X or O1. So like there's not like a non-awkward way to do this, I think. I can just say, if mark 1, then stop. So I'll just say return, and return here means that the game is over, right? Like the function exits. So likewise, and that kind of means that this is kind of a little bit superfluous. I can say something like if the computer won, then I also return. So I do want to print the board as well one last time here. So again, unfortunately, there's not really a non-awkward way to do it. So I'll do it kind of like this. All right.
I have a quick question about, so like, if, okay, this is, again, it's about the midterm, but
Sure.
like, if we have a question like this, where like, if we were working through it on a computer, it would be really convenient to print stuff over and over and over again to see how it changes. Would we have to do that like on a midterm? Because obviously we can't see what's going to happen. So, you know what I mean?
I mean, I do. So like this is kind of both an advantage and a disadvantage, I would say, right? Because well, like and I've had experience with kind of during kind of when COVID, I guess, first started, we did the midterms online and also kind of non-proctored because it was like the Wild West back then. So what we would so what we found is like people are not like necessarily that much happier about doing the midterms on the computer. And that's because like if you do it on the computer and you have access to Python, then there is more of an expectation that the code that you submit actually works, right? Because you had the opportunity to debug it. And like if you didn't
Yeah, that's fair.
and that's kind of the usual thing that happens if you do kind of things in the computer, like if it's on a computer and you also don't require that it actually works, that's just kind of weird, right? So
Yeah,
I
okay.
mean, I
Thank
suppose you
you.
could, but yeah. So when you're writing on paper, like as you see in the marking schemes, like there is not necessarily an expectation that it would exactly run. Right? It's like maybe for like if there's minor syntax errors, then you lose a little bit. If there's like minor logic errors, you lose a little bit. But there's not really an expectation that we're not really saying that like if it doesn't run, then it's a 0. On the other hand, like that would approximately be the case, not exactly, but that would approximately be the case with kind of things that are written on a computer.
Okay, thank you.
Professor,
Mhm.
just a little bit more about the midterm. I'm not too sure if you're allowed to kind of answer these questions, but exactly what would be on the midterm? Like, what units do you expect? Is it going to be something from last week? Is it going to be something up till this week, or?
Yeah, so what I said in lecture is that it kind of officially everything up to Monday is covered. And then what we do on Wednesday is like we don't introduce any new syntax or anything, but we will do some problem solving.
Okay.
So that could potentially be useful because really the course is about problem solving. But technically, we're not going to be introducing new material.
And
Or,
would there
like
also be
in a sense of like new syntax.
and would there also be things related to the Hopfield network?
I don't know. So it would be kind of anything, but certainly kind of anything from lecture, anything from the lab, unless it was explicitly said at the time that it's not included.
Okay.
You know, and like again, like I think like I understand why people ask, like it's a natural question, of course, but at the same time, like I quite strongly feel that like it's not actually like harder than any other material in the class. It just like seems a little bit unusual, but you know, I think it's it's well within well within kind of the bounds of what's in the course. Yeah.
Were the Hopfield networks in the curriculum before he won the Nobel Prize?
No, times change.
Oh, okay, interesting.
No, like that was like a spur of the moment kind of thing. But I think it actually kind
Yeah.
of works kind of nicely with the material in the sense that, you know, like I don't think like the Hopfield network question is like more difficult than the tic-tac-toe question or anything. And they're
Yeah,
using
no,
kind of
that's fair.
the same constructs. Yeah.
Okay, cool.
Thank you.
Yeah. Okay. All right. So we're almost done, right? So the only thing that's left to do is to write something that would use is when in order is when mark. Oh, sorry. Did I actually write as when? I didn't actually write. Okay. So I wrote it as when mark, I guess. So when I said is when over here, I really meant as when mark. Okay, so now what I want to do is I want to lay a move that actually makes sense, right? So I'll say board and mark. And what I want to do is if there is a move that results in an immediate win, then play it. So here's how I'm going to do it. So I'm going to say for row in range 2, and I'm going to say for column in range 2. So I'm going over every possible move. 3. And I'm going to say if board row column is empty, because if it's not empty, then it's definitely not a viable possibility. So if it's equal to space, then I'm going to temporarily say, okay, so board at row at column is equal to mark. So I'm going to try putting the mark in there essentially. And then I'm going to ask, well, does that mean that I won? So I'm going to say, if that means that I won,
Do you need an if before board row call equals?
yes,
Um,
thank you. So I'm
is it-
saying, if this means that I won, then great, I return. Right, so here I don't need to return anything in particular. I just say return. So that's the same as return none, but I could just say return. So that means the function is over. If it means that I haven't won, then I'll keep looking. So I'll say board row column mark is again empty. And then if I haven't found anything, so here, like I've returned if I made a move that resulted in a win. So if that didn't work out for me, then I'll just make a random move. And that's it. So what this function does is it tries every possible move. And then if it turns out that once you place the mark on the board in row column, that resulted in a win, that's it. If not, then you keep trying. Yeah.
Sorry, I don't understand how that function looks for an immediate win. Because to me, all I'm reading is that it's saying if there's an empty thing, play. And I don't.
Well, yeah, except so if there is an empty thing, then play. And then if that's a win, then return. So that's the play, and that stays on the board.
Oh,
If that's
so we
not a
play
win, I
it.
say erase that, and then just move on.
Oh, okay. So your else statement undoes
Yeah.
the first if statement.
Well, so not
Okay,
exactly undoes, but overwrites it back with an M.
yeah. Okay, and then it'll just keep looking. Okay, that's interesting. Thank you.
Yeah. Yeah, that's it. Right. There's like 2 people with their hands up, but I'm not sure if that's from before. That's probably from before.
No, I think your thing is visually glitching.
Say it.
I think your thing is visually glitching a bit because it showed my hand up for a lot
Oh,
of
I
times
see.
that it hasn't been up.
Yeah.
That's okay.
I see. Yeah. Okay. Well, it's now down, so that's good.
Yeah.
Okay.
Thank you so much.
Yeah. My pleasure. Okay. All right. Unless there's questions, I'm gonna go because I'm done.
Okay. Thanks again. See you.
Yeah. All right.
Thank you.
Cheers. Oh, okay. Yeah. So I'll just check Discord. Okay, there's nothing on Discord. That's good. Okay, so I'll be back at 7, I believe. Okay, see ya.